Welcome to the pre-recording of the first half of lecture 4 of computer algorithms, scheduled for the start of the second week in the 8-week summer session. So we are talking about implementing algorithms to traverse graphs. What this means in this course, a course on design and analysis of algorithms, is not that we are going to do some coding, although if you want to do this, it's certainly not prohibited. But what we will be doing, we will be selecting the best data structures for the algorithm. And that is necessary in the analysis to demonstrate the running time, because in this course we are interested in efficient algorithms. Efficient algorithms mean that the running time, in the worst case, is bounded by a polynomial in the input size. So this lecture is structured in two parts. We have introduced in the last lecture two algorithms to compute a tree of all connected nodes, to compute essentially all the connected components. In the first half, in this pre-recording, we focus on the breadth first search. This lecture should be more or less self-contained, except for that we keep on using the same terminology. In the second half of this lecture, the following pre-recording, we look into depth first search and applications of the algorithms. Okay, data structures. So data structures is a prerequisite for this course. So in some sense, traversals most likely will also have been explored in a data structures course. So we are mainly now looking at data structures from a perspective of algorithms. Again, we want efficient algorithms. What is a graph again? A graph is given by two sets. One set of the nodes. A node is also called a vertex. So the dimension there is n, the number of vertices in a graph. And then we have the number of edges, or the connections between the nodes in the graph. So that's a second dimension, a second number, the little m. So we will express, so I talked about the input size, but we will typically express our running times in terms of those two parameters. The n, number of vertices, m, the number of edges. Now, how large can that m be? Well, trees, and we will actually compute trees. Trees are important graphs of types, and we have proven that as a characterization, if we have a connected graph with node cycles, with n nodes, if there are n minus 1 edges, then that is a tree. That's a characterization for a tree. A tree, by the way, is a connected graph where there are no cycles. All right. So the m is linear in n, is about n. The m is thus about n. On the opposite side, we may have a graph that is completely connected. So many cycles you can cycle through all the entire network. In that case, how many edges do we then have? Well, we compute n choose 2, which is here of order, which is bounded by n square. It's 1/2 of n square minus the half of n, but as far as upper bounds goes, asymptotic upper bounds, when the n is growing and growing, then actually we are saying that this is bounded by n squared. So if we look at connected graphs on n nodes, we need at least n minus 1 or order n. So in some sense, I could have used the big omega here. On the upper bound, we have n squared. Okay, so how can we then represent the graph? We have adjacency matrices. So you could say a matrix is just a table of numbers. Here we are going to be a little bit more precise. You can look at the example. We have a graph on 4 nodes. We will have an array of 4 arrays. So we have an array of arrays. And in the adjacency matrix representation, we put a 1. So node 3 is connected to itself. So at the last element, very last element of this matrix, we have a 1 because 3 loops to itself. We have a 0 if there is no edge. The virtue of working with representations like this is that we can query in constant time to see, for example, if there is a connection between vertex 1 and vertex 2. There is none, we can see it, but for a computer needs to go to the first index 1 in the array of lists, and then needs to go to in that array to the second position, to the position with index 2, to see that there is a 0. And this can be done in constant time. So that is the virtue of this representation. If the graph is completely connected, you will see a matrix of ones, essentially. Okay, the adjacency list representation, and here it's worthwhile again to look first at the example, is also an array as long as the number of vertices, so here in this case 4, and every array is a list. So every entry points to the first element in a list. So we see here that the vertex 0 is connected to 1, 2, and 3. So we have a list where we store the labels of the vertices that are adjacent to vertex 0. Here I ordered the labels of the vertices, the names of the vertices in the lists. That doesn't need to be that way. The important property here is that the length of the list is the degree of the vertex. What is the degree of a vertex again? That are the number of connections that the node is involved in. So the degree of the vertex 0 is 3. This is a well-connected node. Vertex 1, on the other hand, has degree 1. So that's a virtue of this representation. Also, the space that it takes is much less for graphs that are not fully connected. Typically in a graph, so you can think of the graph of social relations. I mean, how many people do you really know? That is typically your family and your friends and your neighbors. That's typically constant, whereas the total number of people where every person is a vertex here, that starts to grow. Okay, let's now compare them. Adjacency matrices have an advantage if you want to look up quickly connections. But there are two drawbacks, and these drawbacks will actually make that we will not use adjacency matrices. First of all, the space is tightly equal of order n square. When we want to compute a degree, and that's an important property, we have to go through all the nodes. So we are going to store, suppose that if you, for all the people in the United States, you have about hundreds of millions of them, you want to compute how many people that know a particular person, you have to check hundreds of millions of people. Which is here in this data representation, checking whether there is a 0 or a 1, or adding up the sum of all the elements. Now, again, it keeps in mind that the number of edges that are incident to a vertex tend to be much smaller. In most graphs, the number of edges, is of the same order of n. So that's why it's a huge waste to use an adjacency matrix. Okay, so the arrays of lists is then the data structure that we will use to store both graphs and the trees, because they have the virtue that computing the degree of a vertex is actually computing the length of the list. And since again, the number of edges incident to a vertex is rather small, this can be done in relatively quick time. All right, so here then the formalization of this. Why do we prepare this? Well, the data structure to represent a graph is directly proportional to the sum of the dimensions. So we have n vertices, m edges. We have a tight upper bound on the space required to store that graph. Okay, let's go over this. So you could say that on the examples it was obvious, and I hope it was obvious. So, but let's now formalize this. So in the adjacency list representation, so we always start by spelling out definitions. So we know what is a graph, but we have to spell out what is important here is the adjacency list. So we have an array of n pointers, and we have for every element in that array a list containing the edges. So we have already our big omega of n, and also we have the big omega of m, because remember again, we are storing in the lists all the vertices that are adjacent to the vertex that corresponds to that list. Now, it is important to realize that every edge will occur exactly twice in each list. So if we are for a vertex V, and which adjacent to a vertex W, we have VW. And in the edge list, in the representation of an undirected graph, we write this only once. But here actually we write it twice. We also write it as WV. In some sense, you can say this is rather wasteful, but you could also claim that the adjacency list representation can be used immediately also for directed graphs. So in the it's important then to observe that even if we store every edge exactly twice, 2 times the number of edges is theta, big theta of m. So to recap, we have the array of pointers, big theta of n, where n is the number of vertices. We have then the big theta of m, where m is the number of edges. And we have shown earlier last week in the second lecture that the sum of two big thetas is a big theta of the arguments in the sum. So I simply stated this here, but a more complete proof, I should have actually perhaps be more precise to actually have stated the theorem that we are using to complete the proof. All right, data structures are settled. I was talking about 2 times m, so the 2 times m appears at the very right in the sentence of this proposition. So a proposition is not as important as a theorem, but you could read it as a property that stands on its own. So we're going to use this property to prove that our graph traversal algorithms are efficient algorithms. So this is a very important lemma, if you like, but it also stands on its own. So if you have a graph with m edges, then if you compute the sum over all degrees, then actually the sum of all degrees of all vertices equals 2 times m. And you can actually say, why do you say this now again? It appeared in the analysis of the adjacency list representation. And indeed, so I start out by spelling out the definition of what is the degree of a vertex. And the degree of the vertex is counting the number of edges incident to V. And then we make the same observation that we have made before. Now, within the context of this lecture, we don't spell it out very clearly anymore. If this is a self-contained, if I would have started with this proposition, I wouldn't have copied what I had in the proof of the previous slide. So, but now we are formalizing this in the sum of the degree. Every edge is counted exactly twice. Once when we get to the vertex V, and once if we get into the vertex W. Therefore, the degree of the sum of the degrees of all the vertices equals 2 times m. So by the way, there is a little typo here, and I think it's clear within the context that the argument of the degree function is actually the little v, not the capital V. Okay, done with the data structures. Let's look now at the algorithm. So I'm kind of halfway here. What is the breadth first search algorithm again? So what is the problem that we try to solve? We have 2 vertices, and we have to decide, is there a path between these 2 vertices? Here, the first vertex is called the root node. And the way the breadth first search algorithms works, it layers, it partitions the vertex set in layers. First layer is the start vertex, the root node. The second layer consists of all the nodes that are neighbors of the start vertex. Important is that we do not cycle back. So in all the choices that we have for the S, we must have that there is an edge that leads up to S, but it must also be that we do not consider as a choice for S any of the previous vertices that we have visited. So we start with the neighbors of the root and then the neighbors of the neighbors. And the mathematical notation has the virtue that the definition for the kth layer follows. So it's actually a recursive definition. The start layer is the root, and then for any layer, we look at all the vertices in the vertex set, not in the previous layers. Not, and actually I could have simplified this a little bit by starting with I equals 0. So we look for all the vertices that we haven't encountered yet, and for which there is an edge from a node, from a vertex of the previous layer. So T, we have an edge T of S, so we will include S if there is an edge, and if that edge starts at exactly the previous layer. Okay, this defines the breadth first search tree if we, for every edge, for every two pair of nodes between two layers, we add exactly one edge. So it's important when we ran the example last time that we include uh, only one edge between one node of two consecutive layers. So with the layers, we can organize all the nodes, all the vertices of the connected component of the graph that starts at the vertex R, the root of that tree. So that is the breadth first tree, or the breadth first search tree. Okay, how do we store this now? It is a tree, so we will use the adjacency list representation. So every vertex will be stored. So we will have a list, an array first, um, and then for every edge, we will store the vertices that are adjacent to this edge. So it's important that the adjacency list stores the two edges. So for every node in a tree that is not a root and that is not a leaf, we have exactly two edges. We have the edge from the node up to the parent, which might be the root, and also the edge to the child, which might be the leaf. Okay, the layers actually store all the siblings, all the nodes at the same level in the tree. Okay, we with this breadth first search tree, we actually compute a lot more than saying if we started with the original problem to decide whether for a pair of vertices there is a path. We actually compute all shortest path from the root to every vertex that can be reached from that vertex. You might be worried here a little bit. We had a very simple question to begin with, and actually we compute a lot more. And we keep in mind that we are interested in efficient algorithm. So it's then kind of already uh, aren't we doing way too much work here if we are computing all the shortest paths? Okay, what is now the distance? So the distance is infinite if there is no path between two vertices, and it is the number of edges in the shortest path between the two vertices. So the sentence between the definition and the theorem reformulates essentially the theorem. The theorem is more stated in the language of layers, is more precise. Although if you like more in general, that the breadth first search tree defines all the shortest paths from the root to all the other nodes in the tree. And it is a unique tree. So we talk about the breadth first tree, which is actually not entirely obvious either, because we are picking. So there is so the order in which we pick the nodes is not really fixed. Uh, in practice, we label the nodes, but the labeling with numbers, labeling of the vertices, might be arbitrary. So it's actually not entirely clear that there is a canonical way of doing this, but regardless of that, and this is why the theorem needs a proof, and why it is an important first, it's not the first theorem that we have, but it's an important first property. Okay, the purpose of the lectures is that you know how to start the exercises. So I will tell you the proof of this theorem. There is a number k in there, that's the distance. So you could say that every edge has length 1 here. It's an undirected, unweighted graph, so there are no weights, but we can still count the edges, so the distance makes sense. So we will prove this theorem by induction on k, the number of layers. You can say the first, so if you prove by induction, that's a technique that requires you to follow steps. First step is the base case. You could focus at 0, but that's kind of a trivial case. You could say for k equals 1, the first layer stores all the neighbors of the root node. And that's obviously the shortest way to get to all the neighbors. So there might be many other paths in the graph how you can go from the root node to a neighbor, but if you take the direct edge, that's the shortest way. Okay, then that was the first step in the induction. We have proven the theorem for k equals 1. Then in the second technique, execution of proof by induction, we say the induction hypothesis. We assume that it is true for all layers with index less than k. So in the previous layer, k minus 1, there we have all the vertices, at distance k minus 1 from the root node. So that is the induction hypothesis. In the previous layer, we have all the vertices at distance k minus 1 from the root. And now you state what you need to prove. So now we need to prove that the statement of the theorem in the kth layer, we do have all the vertices at distance k from the root node. Well, how do we do this? How do we see this? Well, any vertex in the layer k is connected to one vertex in the layer k minus 1. So we have one edge between layer k to every node. Every node at layer k is connected to some other node on layer k minus 1. K minus 1 plus 1 is k. So there is a path, and the path is unique, going from that node in layer k to the root node. And most importantly, we have k edges, we have distance k, and this proves the theorem. Okay, let's now formalize the algorithm completely now with data structure. So we have written down the algorithm by definition of the layers. Also, but let's focus on what will be computed as terms of the data structures by this algorithm. Again, if we want an efficient algorithm, so there will be a loop, we have to show that all the steps that are executed, so we have to define the steps that are executable, so that's the point of a computer algorithm. It's executable, and every step runs in constant time if we have a loop. So then it means that if we are executing, if we are looking at the execution time, we count the number of steps, and with the data structures it is complete if all the uh, operations are spelled out. Okay, we need to keep track of the vertices that are visited, and we will use an array for that, the array visited. Why is that? Well, in the algorithm, we have to decide very quickly whether we have visited a vertex already. And the arrays have the benefit. So I was dismissive for the adjacency matrices, but we still have the arrays that we need to make a quick decision, have we visited or not. In the initialization here, we have only the root visited. We have the sets, we have the layers. The layers will be stored by adjacency, by lists, sorry. We have the vertices in the tree. So in some sense, when we set this up, we have the array of adjacency lists. So I'm using here the mathematical notation still. So this is kind of a hybrid. So we are explicitly using indices for the labels of the vertices, and we will proceed layer by layer. What I was meaning by saying a hybrid, when we actually are adding to the vertex set, we are initializing actually the list at position W. And when we are doing this, we are adding the edge, VW. And that is done uh, at two locations in the adjacency list representation, but here it shows up as one instruction. It is important again, do you ensure the correctness of this algorithm? We will make a tree. And you can see this, that whenever we have a new vertex, we also have a new edge. We started out with one vertex already, so we will have one more vertex than we have edges. Recall the characterization. Okay, as soon as one layer, so we are at the kth layer, we're going to use the k+1 layer. So in the definition of the layers, we had done all k-1 layer, and we were computing the kth layer. Here we go from k to k+1. If the k+1 layer is empty, then that means that we have visited all the vertices that are reachable from the root node. And then actually we stop. Otherwise, we augment the counter k and we go one more level up. Okay, we want to show efficiency. So it's important also to realize that it's going to be very bad if the size of the output would be quadratic or even higher. So if what we are computing would not be bounded by polynomial time, then we cannot have an efficient algorithm either. So that's actually the importance of this lemma. So what are we using for data structures? We use arrays of adjacency list to store the breadth first search tree. We have our array of visited nodes, and then we have the layers. So the lemma states that we have a tight bound on the space. That tight bound is actually of order n. So it is bounded by below by a multiple of n and bounded by above by another multiple of n. So that's the definition. So that's actually what you need to show. So when you start that lemma, you actually have to say that you're proving two things. We have a lower bound that is constant times n, and you have an upper bound that is another constant times n. So you start by stating precisely what you do, and then you enumerate that you have three different types of data types. You enumerate this. So the easiest way is probably start with the array of size n. That is already big data of n. But it needs to be there. So actually you need to copy that statement, the second bullet of the output here. For the breadth first search tree, in a tree, every node, if it's not a root or if it's leaf, is actually included in two edges. And they are stored in the adjacency list representation. Every edge is stored twice. So, but here you use the characterization of a tree. We have n minus 1 edges. So we have the leaves and we have the root, but in any way, so you could say that the upper bound is 4 times n. The lower bound would be if every node in that tree would be either the root or it would be a leaf. So, but in both cases, you have the lower bound is n. Then the layers, any layer can actually be of size n, but that would be the case where you have that all the nodes are connected to the root node with a direct edge. And then actually you would still be done. So you should actually look at, so you can say, you can look layer by layer, and you have an upper bound on the size n, but actually you don't really have the lower bound. It might be better to take the union of all the layers and to say that every vertex is visited only once. So every vertex appears in exactly one layer, and that gives you the tightness of the bound. Okay, we have proven properties, lemmas, and theorems. Um, so these were exercises that were kind of theoretical. Here is a more practical exercise. We ran through this example in the previous lecture. So in the previous lecture, you saw the evolution of the breadth first search tree. So in some sense, you can start from that exercise, make all the drawings, copy all the drawings of the evolution of the breadth first search tree. But here you have to start with the adjacency list representation of the graph. So the purpose of this exercise is to reinforce that you know what that data structure is, and also that you run through this algorithm. And carefully write down the evolution of the data structures. So again, you will use an array of lists for the tree. You have the visited, which is an array of 9 elements, and then the layers. If I recall correctly, there were only 2 levels in the tree, so the algorithm doesn't take that many steps. Okay, now I'm almost 40 minutes in. Officially, lectures take 50 minutes, so I can still dwell on the main result on this first part. So keep in mind that we were originally only interested in knowing whether 2 nodes were connected by a path. But with this breadth first search algorithm, it looks like we do a lot of work. But still, the running time of this algorithm is linear in the input dimensions, in the sum of the 2 input dimensions. It runs in time bounded by the number of vertices and bounded by the number of edges, if we work with adjacency lists representations. So this is now a complete proof. We stated the breadth first algorithm completely. So let's do this. So the initializations are linear. So, and that is fine. So we have only one initialization that takes n steps. All the other initializations are constants. So, and it's an important to realize that if you look at the double loop, we go for all vertices in the current layer over all edges. So if we would be sloppy, we would actually say we have n times m. You could say it's still polynomial, but note that the m can be quadratic in n. So the total running time is cubic in the number of vertices. And that doesn't scale very well for huge graphs. So think about millions and millions of nodes, billions nodes. Not a good idea. So this is also to indicate that this is an important major theorem and that the proof is also gives, and knowing the proof actually gives important insights in this algorithm. Okay, so observe that every vertex appears only once in the layer. So even though we go over all layers, we will do this only once. And if we go over all the edges, it could be just as bad as going over all the vertices, but actually with the adjacency lists, we are going as many times for each vertex as the degree. So the number of steps in this double loop is actually the sum of the degrees over all the vertices in the connected component of the graph. Okay, now that double loop is inside another do loop. Now it's important that this is for all runs of the double loop. So you could say, but wait, does the depth of the tree not come into play here? So you don't see a logarithm in there somehow, a logarithm of the number of vertices? No, because no. So what you have here is that because every vertex appears only once in that layer, I highlighted this in red. This implies that the sum of the degrees actually bounds all executions, all over all layers during the runtime of the algorithm. So that is the important crux of the number of steps. And that is also why we need that proposition. So that important property that the sum of the degrees is actually exactly equal to 2 of m, which is the bounded, again, an order of m. To complete the proof, we have to examine the costs of all the data structures. So when we check whether we have visited an element, that can be done in constant time very quickly, one operation. Um, Inserting an element to the list is also constant time. It's important that you have done or that you will do the exercise in data structures of one of the previous implementation lectures. So if you insert an element in a list, in order to show this, you would spell out all the assignments, all the pointer assignments that you need to do. So in a very similar fashion, so we have the adjacency list representation. Updating that, inserting a new edge is also constant time. So all the statements in that loop are actually in constant time. So we actually do have the double loop is proportional. So again, the top here, the proposition, the property, we have the m. And the sum of two functions bounded by n and m is bounded by the n plus m, by the sum of the arguments. Okay, we have accomplished with this theorem an important analysis of this graph traversal algorithm. So it is a very efficient algorithm. So working with graphs, so running through all the nodes and the connected components in a graph can be done very quickly. So these are algorithms that scale very well. Okay, if you are interested in making it more efficient, so we are practical people after all, so you may not care about all those layers. And you could say they occupy, essentially, we double the number of vertices again, storing them again. We may not need that partitioning of the vertex set into layers. Then we can do with a queue. So queue is what was studied um, many times in data structures. So we essentially, when we go from layer to layer, we only need the previous layer to compute the edges in the breadth first search tree. We already have stored all the edges that we have visited in this visited data structure. So there is no problem. We don't really need to know the elements in the previous. So we will have two queues, the queue with the current layer and the queue for the next layer. So each time, actually, we will then store only a subset of the nodes as this algorithm runs. No more than what could be in the union of two layers. Now, in any case, so it could be, you could have a case where the layer could contain almost all nodes except the root. And the exercise asks you to give an example. In some sense, there are many exercises that are always collected, but this is an exercise that is also quite straightforward. You have a graph where all the nodes are connected to the root node. And there actually the algorithm runs very quickly. And that optimization here doesn't really matter. Okay, so this concludes the first half of lecture 4. In the second half, we will examine the depth first search algorithm, and we will look into two applications of the breadth first and the depth first search of the graph traversal algorithms.